Welcome to the deep dive. Today, we're going to tackle something really core to Java, especially if you're, prepping for interviews or just want to solidify your skills as a senior dev.
Absolutely. We're talking about variable scope in Lambda expressions.
Exactly. How do they play with variables outside their own little world? It's crucial stuff.
It really is. And it comes up a lot, not just in interviews, but in day-to-day coding. So we'll break down the rules, look at some code, and hit those common questions.
Perfect. Let's dive right in then. First things first. Inside the Lambda itself, that block of code, what are the rules for scope within that body?
Okay, so think of a Lambda's body like any other nested block of code you'd write, like inside an if statement or maybe a for loop.
Ah, okay, so the usual rules apply.
Pretty much, yeah.
Yeah.
The main thing is name conflicts and shadowing. You can't, for instance, declare a parameter in your Lambda or a local variable inside it that has the same name as a local variable that already exists right outside it in the method where you're defining the Lambda.
Right, that makes sense. Prevents ambiguity. Do you have an example where that might bite someone?
Sure. Let's say you have in first equals 0, already defined in your method.
Okay.
Then you try to write a comparator Lambda like this. Comparator string comp, open parenthesis first, comma second, close parenthesis, arrow first, dot length, open parenthesis, close parenthesis, minus second, dot length, open parenthesis, close parenthesis, semicolon.
Ah, I see the problem. You used first as a parameter name in the Lambda.
Exactly. And because there's already a local variable named first in scope, the compiler will complain. It'll say something like, variable first is already defined.
Okay, so just like you can't declare intex equals 10, in the same method scope, you can't reuse a local variable name as a Lambda parameter or a Lambda local variable. Simple enough.
Precisely.
Now, what about this keyword? That can sometimes be tricky. How does this behave inside a Lambda?
Ah, good question. This is actually a key difference compared to, say, old school anonymous inner classes. Inside a Lambda, this does not refer to some new instance of the Lambda function itself.
Oh, so what does it refer to?
It refers to the this of the enclosing context. Usually that means the this of the object whose method contains the Lambda definition.
Okay, walk me through that, maybe with an example.
Yeah, let's imagine a class, say application.
Right.
Public class application open brace. And inside it, a method. Public void bork, open parenthesis, close parenthesis, open brace.
Right.
And in dogwork, we create a runnable. Runnable runner equals open parenthesis, close parenthesis, arrow, open brace, maybe some other stuff. System.out.print, open parenthesis, this dot toString, open parenthesis, close parenthesis, semicolon, and then close brace, semicolon, and then maybe we use runner. Close brace for the method, close brace for the class.
So inside that Lambda, we're calling this .toString, whose toString gets called.
It's going to call the toString method of the application object, the specific instance of application where the dowork method was running when that Lambda was created. It's not related to the runnable instance at all.
Got it. So this just keeps its meaning from the surrounding method. No special Lambda magic there.
Exactly. It's consistent.
All right. Now for the really interesting part, I think. Accessing variables from outside the Lambda from that enclosing scope. How does that work?
Right. This is where we talk about capturing variables, sometimes called free variables. These are variables the Lambda uses that aren't its own parameters and aren't defined locally inside its body.
Okay. Like in a setup method, perhaps.
Yeah, consider a static method like repeat message. Public static void repeat message, open parenthesis. String text, comma, in count, close parenthesis, open brace.
Okay. Takes a message and a repeat count.
Yep. And inside, we create a runnable. Runnable R equals open parenthesis, close parenthesis, arrow, open brace, and then a loop. For open parenthesis, in I equals 0 semicolon, I less than count semicolon, plus at, plus close parenthesis, open brace. And inside the loop, system.out, println open parenthesis text, close parenthesis, semicolon, then close brace for the loop, close brace for the Lambda body, semicolon.
Okay, so that Lambda's job is just to print the text variable count times.
Correct. And then maybe we start it in a new thread, open parentheses, R, close parenthesis, dot, start open parentheses, close parenthesis, semicolon, and close brace for the method.
So the Lambda is using text and count, but those are parameters of repeat message not defined in the Lambda.
Exactly. They are free variables from the Lambda's perspective.
But hang on. The repeat message method could finish running, right? Its stack frame disappears. How does the Lambda, potentially running later in a different thread, still know the values of text and count? It feels like they should be gone.
Ah, that's the magic of variable capture. When the Lambda expression is created, it takes a snapshot, essentially. It captures the values of those free variables it needs.
Captures the values.
So if you call repeat message hello 1000, The runnable object R that gets created internally stores the value hello and the value 1000.
So it's not capturing the variables themselves like a pointer, but the data they held at that moment.
Precisely. The internal structure representing the lambda holds copies of or references to these captured values. This mechanism allows the lambda to execute correctly later, even if the original method context is gone.
And this whole package, the Lambda code plus the captured values, this is what people mean by a closure, right?
You got it. Java Lambda expressions are closures. They close over the variables they need from their defining environment.
Okay, cool. But there must be some rules around this capture, right? It can't be just anything.
Absolutely. And this is a really important one, especially for interviews. The rule is a lambda can only capture variables from its enclosing scope whose values do not change after they are initialized.
Don't change. So they have to be final.
Either explicitly declared final or what we call effectively final.
Effectively final, meaning?
Meaning the variable could have been declared final without causing a compile error. Its value is assigned once and never reassigned later in the scope.
Okay, so it doesn't have to have the final keyword, but it must behave as if it did after its initial assignment.
Exactly. The compiler checks this.
What happens if you try to capture a variable that isn't effectively final, like one that gets modified later?
Compile time error. Classic example.
Yeah.
Trying to capture the loop counter in a standard for loop.
Ah, yeah.
Imagine this.
Yeah.
For open parenthesis, and I equals 0 semicolon,
Yeah.
less than and semicolon, I plus close parenthesis, open brace.
Mm-hmm.
And inside you do new thread, open parenthesis, close parenthesis, arrow system, println, open, close parenthesis, dot start, open parenthesis, close parenthesis, semicolon, close brace.
So you're trying to print the value of I in a separate thread for each iteration.
Right. But the compiler will stop you. It'll say something like, variable I access from within inner class needs to be final or effectively final, because I changes I++. With each loop iteration, it's not effectively final. There isn't one stable value for the lambda to capture.
Okay, that makes sense. The value is constantly changing. But wait, what about the enhanced for loop, the for each loop? I feel like I've seen captures work there.
Good point. That's a subtle but critical difference. An enhanced for loop is different. Consider, for open parenthesis, string arg, :args, close parenthesis, open brace, new thread, open parenthesis, close parenthesis, arrow system, dot out, dot, open parenthesis, close parenthesis, dot start, open parenthesis, close parenthesis, semicolon, close brace.
Okay, looping through command line arguments, maybe?
Yeah. And this is perfectly legal. You can capture arg.
But why? Isn't arg changing in each iteration too?
Not quite. The way the enhanced for loop is defined, you can think of it as creating a new, fresh arg variable for each iteration. That new arg variable is assigned the next element from args. And within the scope of that single loop iteration, that specific arg is effectively final.
Whoa. Okay, so each lambda captures a different arg variable, one for each iteration, and each of those is effectively final within its own little loop cycle.
Exactly. It's a neat detail of how the enhanced for loop works under the hood.
That's a really useful distinction. Okay, so we have this effectively final rule. What's the biggest implication? Does it mean you can't change a captured variable from inside the lambda?
That's the core consequence, yes. A lambda cannot mutate or reassign a captured local variable.
So you can read it, but you can't write to it.
Precisely. Let's tweak that repeat message example slightly. Say we want the lambda itself to decrement the count. Public static void repeat message, open parenthesis, string text, comma, int count, comma, int threads, close parenthesis, open brace. We set up our runnable R equals open parenthesis, close parenthesis, arrow, open brace. And inside maybe a while loop, while open parenthesis count greater than 0, close parenthesis, open brace, and here's the problem line. Count minus semicolon, then system.out.println, open parenthesis text, close parenthesis, semicolon, close brace for the while, close brace for the lambda, semicolon, and then start some threads using R.
Okay, so inside the lambda, you're doing count at set, trying to modify the captured count.
Yep, and that's a compile time error. The compiler enforces the effectively final rule. You can't mutate count because it was captured from the enclosing scope.
Makes sense. It prevents the lambda from changing the state that was captured. And I guess this has benefits, right? Especially with threads running.
Huge benefits, particularly for concurrency. By preventing lambdas from easily modifying shared local variables captured from the outside, Java avoids a whole category of potential race conditions right at compile time. If multiple threads running the same lambda instance could all modify count without any locks, well, you'd get chaos.
Right, unpredictable results. So the rule kind of pushes you towards safer concurrent patterns, even if that's not its only purpose.
Definitely. It encourages a more functional style where you work with immutable captured state.
Okay. Now, are there ways people try to kind of work around this? Like technically follow the rule, but still achieve mutation? I feel like I've seen some hacks.
Yeah. Yes, there are ways, but they often come with big flashing warning signs. The classic one is using a single element array.
An array, how does that work?
Like this. Int open bracket close bracket counter equals new int open bracket 1 close bracket semicolon. So you have an array holding one integer.
Okay.
Then maybe you add an action listener to a button. Button dot, add action listener open parenthesis, event arrow counter open bracket 0 close bracket plus plus close parenthesis semicolon.
Ah, so the Lambda is doing counter 0 plus plus vo. It's changing the content of the array element.
Exactly. Now, why does this compile? Because the counter variable itself, the reference to the array, is effectively final. It's never reassigned to point to a different array.
Right. The Lambda captures the array reference, which is constant, but it can then use that reference to modify the array's contents.
Precisely. It's a loophole, technically speaking. The variable counter is effectively final, satisfying the rule, but the state reachable through that variable is mutable.
But you said warning signs. Why is this usually bad?
Because it completely sidesteps the safety the effectively final rule provides, especially in multi-threading. If multiple threads execute that lambda, counter 0 plus plus, you're back to having a race condition on counter 0. You'd need explicit synchronization, which complicates things. It's generally considered, well, a terrible idea unless maybe for very simple single-threaded UI updates or similar niche cases.
Got it. So technically possible, practically dangerous most of the time. Avoid unless you really know what you're doing and why.
That sums it up perfectly. Stick to the effectively final principle for captured locals.
Okay, great. Let's quickly recap the main takeaways then. We've got scope inside a lambda is like a normal nested block.
Yep. Standard naming rules apply.
This inside a lambda refers to the this of the enclosing instance, not the lambda itself.
Correct. Consistent with the surrounding method.
Lambdas can access or capture variables from the enclosing scope. These are closures.
They capture the value at the time of creation.
And the huge rule. They can only capture local variables that are final or effectively final, meaning their value doesn't change after initialization.
The big one. Effectively final.
Which implies you cannot modify or reassign a captured local variable from within the lambda.
Right. Compile error if you try.
And trying to work around it with things like single element arrays is usually risky.
Very risky, especially with threads.
Awesome. That really clarifies the landscape of variables and lambdas. Understanding these rules feels fundamental for writing clean, modern Java, and definitely key for those technical discussions.
Absolutely. Nail these concepts down, and you're in a much better position whether coding or interviewing.
So as a final thought for everyone listening, thinking about this effectively final rule, what does it suggest about broader design? Considering this constraint, what kind of design patterns or maybe programming techniques do you think naturally fit well with this? You know, approaches that maybe lean into this immutability aspect and help create more robust, predictable code when you're heavily using lambdas? Something to chew on. Thanks for this fantastic deep dive.
My pleasure. It's a crucial topic.